Let's talk a little bit about stoichiometry. A little bit of this should be a review from general chemistry, but let's get up to speed on some of the topics that we're going to be using in analytical chemistry. Here's a little concept. Map stoichiometry is defined as the quantitative relationship between reactants and products, and it assumes that that atoms are conserved, so that if we start off with so many carbon atoms, we have to end with so many carbon atoms. This assumption is typically valid unless we are talking about something like nuclear explosions. So please do not do any nuclear chemistry in the lab when you are working with stoichiometry. We often use a balanced chemical equation for performing stoichiometry, although we are going to see a couple cases where it is not necessary to have a completely balanced chemical equation. In the first example, though, we'll take a look at, say, the respiration of glucose. So C6H12O6 is glucose. There's respiration involves, or aerobic respiration involves the reaction of glucose with oxygen to form carbon dioxide and water. And you should remember from balancing chemical equations that we can't change the subscripts in the molecule, or else it changes the molecule. We can only change the coefficients in front, and in this particular one, if we set 6s to each one of the oxygen, carbon dioxide, and water, we get a balanced chemical equation where the same number of atoms are on both the reactant and the product side of the equation. Last important concept about stoichiometry is that we need to do all of our calculations in moles. So usually we are in the laboratory where we are measuring either a volume or a mass, and one of the very first things that we will do, the first calculations that we do in stoichiometry, is convert those experimental measurements into moles. So let's take a closer look at our example here. We've got glucose, which is reacting with oxygen to form carbon dioxide and water, and the question would be how much oxygen is consumed in the combustion or respiration of 13.5 grams of glucose. So we have, in general, a process that involves answering three questions. Where do we start? Where do we end? And then how do we get there? These are the three general questions that we're going to be answering in any sort of stoichiometry problem. In this particular case, we see that we're starting with only one, there's only one number there that we're starting with, so we're going to start our calculations with this 13.5 grams of glucose. And what we want is an amount of oxygen. Now, I didn't clarify that in the problem. If this was like a quiz or something like that, I would need to do that. But let's say that I want grams of oxygen. Let's assume that the problem was actually described a little bit more detail. And I want grams of oxygen. The how do we get there is our stoichiometry, and we can sort of plan this out, where we need the grams of glucose. We're going to need to go to moles of glucose, then the moles of oxygen, and then from that we should be able to get to the grams of oxygen. So there's our plan. In all of these cases, or in the first steps here, we're going to need molecular weights to be able to convert from masses to moles. It'd be a great idea for you to pause the video at this point and figure out, or make sure that you know how to find that information on your own. For the molecular weights, I get 180.16 For glucose, 32.00 for oxygen, and might as well do the others, 44.01 for carbon dioxide, and 18.02 for water. And all of these would be in grams per mole. So we can go ahead now and start crunching some numbers and develop our plan using the 3 questions that we've got. We're starting, so I'm going to put over here on the far left 13.5 grams of glucose, and I'm going to use a capital G to represent glucose so I don't have to keep writing that out. And then we're ending, I'm going to put as far over to the right as I can so I have all the space that I need, so many grams of oxygen. So that's where I'm actually trying to find, where I'm trying to get to. So the first thing I need to do is get rid of the grams of glucose, and using the molecular weight, I can convert that into moles of glucose. And I know that there's, from the molecular weight, 1 mole of glucose is 180.16 grams. We take a look here, and that gets rid of that unit. Now I keep on going because that's not a number that I need. I can use the chemical equation now to get rid of moles of glucose and convert that into moles of oxygen using the chemical equation. The coefficients in front of each one of these molecules are 6 and 1 respectively. When I do that, I get rid of moles of glucose. And then the last thing that I need to do here is convert the moles of oxygen into grams of oxygen, because that's the unit that I'm interested in. So I will put in moles of oxygen in the denominator, because that's what I'm trying to get rid of. And the units, or the numerator, is 32.00 grams of oxygen for 1 mole. I see those numbers cancel out, and I'm now at a point where the units of my calculation are going to be the units of my answer, and so I can go ahead and plug these numbers in my calculator, and when I do that, I get 14.39 grams of oxygen. So if we take a quick look at the number of sig figs, my molecular weights all have 4 sig figs in them, except for the glucose, it has 5. So there are at least 4 sig figs there. However, my starting only has 3 sig figs. So that means that I need to round off my answer to 3 sig figs, and that gives me 14.4 grams of oxygen as my final answer. Let's take a look at an example where we don't need a complete balanced chemical equation. So in this particular case, we're going to use as an example the analysis of this compound called disulfiram. Disulfiram is a medicine that is used to deal with patients who are struggling with alcoholism. To make a long story short, it makes you feel absolutely violently ill with the slightest amount of alcohol intake. So in this particular example, what we're doing is performing an analysis of disulfiram, of a tablet, to see if what the purity of the particular tablet is. I'm not going to go through a lot of details here, because if you take a look at the Harvey or your textbook, chapter 2, this is example 2.7, and so you should go ahead and take a look at it, because there are some details that I'm skipping. Some conversions from acids to bases and milliliters to grams and whatnot that are good practice but are not relevant to the stoichiometry that we're doing right here. we don't have, or in the analysis, what happens is the molecule disulfiram is converted into sulfuric acid, and then the titration is performed to analyze the amount of sulfuric acid that is present. We don't have an exact balanced chemical equation for this digestion, but we do know that the only compound that contains sulfur in the reactant side is the disulfiram, and the only compound that contains sulfur on the product side is sulfuric acid. So regardless of what the other types of molecules are in the complete balanced equation, we know that one disulfiram is going to create 4 sulfuric acid molecules, because we see that there are 4 sulfurs here, and there's obviously only 1 sulfur in sulfuric acid. So regardless of what the rest of the chemical equation is, we know the ratio, the stoichiometric ratio of disulfiram to sulfuric acid is 1 to 4. So we can proceed with this analysis without knowing the complete balanced chemical equation. And we've got some information here that I pulled from the exercise. The sample is 0.4613 grams. In the analysis, we determined that there was this many moles of sulfuric acid detected, and I've already crunched the molecular weight of disulfiram for you, so we should be able to proceed here. We've got 3 numbers. Remember, we need to ask ourselves 3 questions. Where do we start? Where do we end? And how do we get there? Since we've got 3 numbers, we need to figure out which number we're going to be starting with. And it makes sense for us to start with the moles of sulfuric acid, because the grams of sample is part of the problem that we're trying to solve. We know how much of the sample was that we had, but we don't know how much of that was disulfiram. So that is not a useful quantity for us. And then since the molecular weight is a complex unit with units in the numerator and denominator, it's going to make better use as a conversion factor. So we're going to start with 4.3562 times 10 to the minus 4 moles of H2SO4, and we want to end in we're going to want grams of disulfiram. I'm going to abbreviate that DS, because we're going to figure out how many grams of disulfiram were in the sample, and then we can take the ratio of those 2 numbers to get our answer. Okay, so now we know we have a strategy now for how we're going to get there. We need to get rid of the moles of H2SO4, 1 mole of disulfiram, that gets rid of moles, and then we can use the molecular weight, 296.54 grams of DS and 1 mole of DS. When we crunch that number, we get something along the lines of 0.3, I lied, 0.03229 grams. Now, if we take that number, so this is the mass of disulfiram that was found in the sample. So if we want to know how much of the sample is actually disulfiram, we use part over whole for that. And we would take 0.03229 grams of disulfiram over 0.4613 grams of sample. And if we multiply this by 100 to get our percent, we're going to get something around 7%. So this gives you a little overview, so a review of basic stoichiometry concepts. And in this last part here, some of the shortcuts that we're going to be using in analytical chemistry, mostly because we won't have access to or we won't care about a complete balanced chemical equation. The key is knowing what the stoichiometric ratio is between the reactant of interest and the product of interest, in this case disulfur-M and sulfuric acid, and making sure that the analytical process does not involve sources that could complicate matters. In this case here, if we had another reagent that had sulfur in it or another product that had sulfur in it, we could not do this process. We would need to know more information about the chemistry. So the analytical process is designed to help us minimize those types of challenges.